Okay, this morning we're going to keep talking about perceptrons. And we're going to keep working with the kind of toy example from last time. I mean, obviously it's very simplified, but nonetheless gives a good idea. Will give us a good idea of how these are working. So remember, just what is a perceptron? So these are attempts to create a kind of an artificial neuron. And as we'll see next week, they're going to be the building blocks of more complicated algorithms, which we're going to call neural networks, which essentially, as the name suggests, network together perceptrons. So the basic building blocks. Or we'll eventually introduce neural networks. Okay. So what we're going to do, as mentioned, we're going to keep working through this example to kind of get an understanding of how these are working. Then we'll introduce some mathematical notation, some formulation for them, and then we'll look at some more examples, talk about them a little more. Okay, so what was the example we were talking about last time? Let me just write so we are deciding whether or not to attend a wine festival. And the way we've set this up is we've used a fairly simple setup where we have a binary output. So let's start with the output. And the output is our decision. And there's only two options. So that's what I said by binary. It's a binary decision. We go, and then we're going to indicate that with a 1. We'll encode it numerically, or we don't go. And we'll encode that with a 0. Okay. So in some sense, we're doing a binary classification problem, but we're using 1s and 0s as our classification. And then the inputs were also binary, and there were 3 of them. So there are 3 considerations. Those are essentially are going to be our features here. And the considerations are binary as well. They're yes or no questions. Okay. So the first was, is there going to be good weather? And we denoted this feature by x1. And just like before, we're going to encode it using 1s and 0s. Yes or no correspond to a 1 or a 0. The second, was it accessible by transit? And this also, of course, encoded by a 1 and 0. And then the third was there food available? That'll be x3. Okay, so generally speaking then, the binary encoding here is that xj is going to be equal to 0 if no, and then 1 if yes, for j equals 1, 2, and 3. Okay, so each of our features, in this case, our variables, consists of a binary response, a yes or no response. So they can only output, the inputs are going to be 1s and 0s, but then the idea is that we can weight these, multiplying them by constants to change their relative values. So next what we do is we assign weights W1, W2, W3 to each of x1, x2, and x3 corresponding to the relative importance of that factor in the decision-making process. And then we set a threshold B, and we'll talk a little bit more about what the threshold represents a little bit later. But for now, just think of the threshold is going to determine how the sum product, so the net input, where we incorporate the weights, how that corresponds to the output, how that determines the output value. Okay. So our output is still going to just be a 0 or a 1, so it's the same as before. So 0 for don't go, 1 for go. But and the way it's determined is if we take the sum of the weights times the input variables. If that's less than or equal to threshold B, we'll call that, so the B is the threshold, then we don't go. If the net input, the weighted sum, is greater than the threshold, we do go. So just as a reminder of that name, so the sum of the weights times the corresponding variables is the net input. And we'll formally define that a little bit later. Okay. So last time, I won't repeat it, but we looked at what we called scenario 0, which is we only go if all 3 factors are answered with a yes. So in other words, there's good weather, accessible by public transit, and there's food available. And so we saw the one way to implement that was to simply set all the weights to be 1 and then set a threshold of 2, so that we need all 3 variables to equal 1 to surpass that. Let's talk about a slightly different scenario. We'll call this one scenario 1. Okay. You decide to go if and only if the weather is good. So in other words, if the weather is good, you're going to go, and if it's not good, you're not going to go. So that's your single decision making factor. Okay. So there's a few different ways we could implement this. Okay. And so the choices I'm going to make are going to be rather arbitrary, and that's fine. But we'll discuss later on kind of how changing these various factors, the bias and the weights, change the result. Okay. So one way to implement this would be as follows. Okay. So I'll set the bias to be 5, and I'll set the first weight, the one corresponding to the weather, to be 7, and the other 2 weights to both be 2. Okay. So now if we look at the weighted sum, this is going to give me 7x1 plus 2x2 plus 2x3 as my net input. And we can consider this. This is equals. This is greater than or equal to 7 if x1 is equal to 1. Okay, so regardless of the other 2 values, if x1 equals 1, if the weather's good, then the net input is at least 7. Okay. And it's less than or equal to 4 if x1 is 0. Okay. So if x1 is 0, the most it could be is 4, and it could be less than that. So the output is So remember what the bias we set was 5. So the output is 0 if the net input is less than or equal to 5, and it's 1 if the net input is greater than 5. But because of the observations made here, that exactly corresponds to, it's going to equal 0 if x1 is 0, and 1 if x1 is 1. So in other words, if the weather is not good, then it's 0, so we don't go. And if the weather is good, it's 1, so we go. Because in that case, if the weather is not good, the value can never exceed the threshold. It can be at most 4, which is less than 5. And if the weather is good, the value of net input is already 7. Okay. So this is exactly the decision process we want, right? So this encodes the scenario that we described. So we described it in words, and we've seen then that the perceptron can recreate that decision-making, the choice of decisions. Okay. All right. We'll come back to this in a little bit, including how we can represent it in a more compact way using a diagram rather than all this writing. But let's go on to another. Let's look at a few more scenarios just to get an idea of how these different aspects of the perceptron are playing together. Okay, so scenario 2 is going to be the following. You decide to go if the weather is good. Or, okay, so now we have another possibility. If the weather is bad, but the festival is both accessible by transit and has food available. Okay, so the idea is now your sort of preference set, so to speak, is a little bit more relaxed. You'll still go as long as the weather's good, but if it's not good, you're willing to go so long as some other factors, the other two factors, are satisfied. Okay. All right. So let's keep the bias to be 5. Okay. All right. So what would the threshold? Rather, we're going to conventionally call this bias, which is why I'm using B. But so if I say bias, I'm referring to the threshold. So let's keep our threshold to be 5. But now set let's set W1 to be 6, W2 to be 3, and W3 to be 3. So let's consider then what does our net input look like here. It's 6x1 plus 3x2 plus 3x3. Okay. And this has the following property. It's greater than or equal to 6 if x1 equals 1, right? So as long as if x1 is 1, then it's definitely at least 6. Or x2 and x3 are both 1. So regardless of the value of x1, if x2 and x3 are both 1, then it's equal to at least 6. Okay. But it's at most 3 if x1 is 0 and x2 equals 0 or x3 equals 0. So at least if one of the other two is 0, if x1 is 0 and one of the other two is 0, then the most it could be is 3, because then of course it's either 3 if the other one is 1 or 0 if all three of them are 0. Okay. So the output is in this case, what do we get? So it's 0 if the sum of the weighted sum, the net input, is less than or equal to 5, and it's 1 if the net input is greater than 5. Okay. And based on the observations we just made, that is exactly when it's 0 if x1 equals 0 and xj equals 0 for j equals 2 or 3. Okay. And it's 1 if x1 equals 1 or x2 and x3 are both equal to 1. And so just as before, this does exactly what we want, right? It encodes the decision-making process described in the scenario. Okay. Let's tweak things a little more. Okay. So the festival was moved inside, moved indoors. So you no longer care about the weather. Okay. You'll attend. If it's accessible by transit, or has food. Available. Okay, so now your sort of preference set has weakened, right? You don't care at all about the weather, and then of the other two factors, you only require at least one of them to hold. Okay. Okay, let's keep the threshold at 5. And this time we're going to set the following. We'll set W1 to be 1, W2 and W3 to both be equal and both be 6. Okay. So now our net input is x1 plus 6x2 plus 6x3. And so we can see that it's greater than or equal to 6 if x2 equals 1 or x3 equals 1. And it's less than or equal to 1 if those two factors are both 0. And then with the threshold still being 5, I'll skip a step this time just in the description. You can see then what how the net input corresponds to this. So the output now is going to be 0 if x2 and x3 are both 0, and 1 otherwise. Okay. So what does this mean? It means that if there's no food and no transit accessibility, you're not going to go. And if at least one of those is true, you are going to go. So the weather doesn't matter at all in either case, which is exactly, of course, what we wanted. Okay. Okay. And so let's move on to one. We'll do one more of these. So now what we're going to see is we're going to take the previous scenario, strengthen it a bit, make ourselves a little more selective as to when we go, and we're going to keep the weights. We're going to see what happens Notice the first three, what we did was we kept the bias the same in all three of them, and we adjusted the weights. Okay. Now, what happens if the weights stay the same, but we adjust the bias? Okay. So again, you don't care about the weather. Since the festival moved indoors. Has moved indoors. Yeah, try to straighten this out a bit. Okay. But now, you'll only attend if it's transit accessible and has food available. Okay. So yeah, so you've got a slightly more restrictive setting here than scenario 3. Okay. So as mentioned, let's keep the weights the same. As in scenario 3. So W1, the weight for the weather, which doesn't matter, is 1. W2 is 6. And W3 is also 6. Okay. Notice that now threshold B equals 5 does not work to implement this decision-making process. Okay. Why? Well, as you can see, so because the net input is greater than 5, so long as 1 of x2 or x3 is 1. But we don't need both. Okay, so that doesn't describe the scenario given here. So for instance, if it was transit accessible but didn't have food, this would output a number of at least 6, and so you would go. But that's, of course, not what we want. Okay. So what we're going to do then is raise the threshold. Okay. So instead, let's set B equals, I'll just do 8. There's lots of choices that would work, but this is fine. Okay. So the net input, as before, is x1 plus 6x2 plus 6x3. And this has the property of being greater than or equal to 12 if x2 and x3 are both equal to 1, and less than or equal to 7 if x2 equals 0 or x3 equals 0. Okay. So notice then, yeah, so if one of them is 0, the other one can be at most 6, and x1 can be at most 1, so that would be most 7. Okay. Okay. So then the output is going to equal, well, it's going to be 0 if x2 equals 0 or x3 equals 0. And it's going to be 1 if x2 and x3 are both 1, which of course is exactly what we wanted. We're going to only attend if it has accessible by transit and has food. Otherwise, we're not. Okay. So remember that scenario 1 was, in some sense, the most restrictive of the first two. Remember, we'll only go if the weather's good. We're going to go if and only if the weather's good. Scenario 2 said we're going to go if the weather's good, but we'll also have some conditions where we go if the weather's bad. Okay. So let's make a couple observations. Okay. So observations from scenarios 1 and 2. At a constant threshold, increasing the values of the weights, depending on, in that case we did 2, but I mean even for just a single one it may change, can make it easier to output a 1. Okay. So larger values of weights then made it easier for, of course, just we're not saying anything very profound here. All we're saying is if we increase the size of the net input function, it makes it more likely to pass the threshold. Okay. And so that corresponded then to an increased willingness to attend. Okay. Now, an observation from scenarios 3 and 4 is the same thing applies in the other direction. By which I mean holding the weights constant a lower threshold corresponds to an increased willingness to attend. Okay. And again, what that means is it is easier to output a 1. Just okay. So what's going to happen then is in the actual sort of the algorithmic formulation of this, both of these are going to kind of be taken into consideration. And in particular, this is kind of getting more into like the next 2 weeks. When you train and tune this sort of algorithm, this is all happening kind of automatically, right? You're not having them do the manual weight adjustments that we're doing here. We're just trying to understand how these changes are affecting what happens. Okay. But all of this, of course, is going to go on in the background, and you're going to be tuning both the threshold and the weights on the inputs at the same time. So then, when you're changing both of them, of course, there can be much more complicated and perhaps much more subtle interplays going on, which is fine, of course. Okay. All right. So let's go through the mathematical description. It will allow us to kind of encode this information more systematically. And also what we'll be able to do is we'll be able to draw a perceptron diagram of the type that we saw last time. Okay. Now, just to be clear, this mathematical description is going to be for what we're going to call a basic perceptron. And the big thing that makes something a basic perceptron, as discussed last time, is we're using this binary output, 0 or 1, depending on whether we're above or below the threshold. Okay. One of the major changes that we'll make going in as we get deeper into the theory over the next couple of weeks, is to change the way the output can be generated by introducing this idea of an activation function. So we're using an activation function here without actually saying it, and we'll see this. But when we allow that to become something a little more complex, it changes the behavior of the output in desirable ways. Okay. All right. So our basic idea is still going to be that if the net input is greater than the threshold, that should correspond to outputting a 1. Okay. And we are going to change the notation a bit. Okay. All right, so let's just let's sort of vectorize this, so to speak. So let's turn the weights into a vector. Let's introduce some linear algebra notation, which of course is useful when it comes to encoding things numerically, right? I'll use P since that's the features. We're encoding things computationally. So when we actually if we want a computer to do this, it's helpful to have it kind of in matrix type notation. And same thing with the features. So we'll encode the features as a vector, x1, x2 up to xp. Then the net input function, that's simply the dot product, right? W dot x, which is by definition exactly the sum product we're talking about. The sum from j equals 1 up to p of wj times xj. And as we were doing in our example, let's use b for the threshold. But as I alluded to, we call this the bias. Okay. So then we can rewrite this a bit. The output that we've been looking at in our example is given notationally as follows. All we've done here is made it a little easier. We don't have to write in the summation notation every time. So it's going to output a 0 if w dot x is less than or equal to b, and it's going to output a 1 if w dot x is greater than b. Okay, so what we're going to do now is just rewrite this a little bit. We're going to move the b over to the other side, so then our threshold, in some sense, our decision boundary is just going to be 0 all the time, which is nice, right? So less than or equal to 0, greater than 0. But we'll also just change notation a little bit. Okay. Rather than using a positive number for this, we'll use a negative number, so that when we move it over to the other side, it's positive. Well, it'll be a plus sign. Okay. So replace. Here's what I mean. Okay. Replace b by negative b, and so the idea is we will use a negative number for the bias. And and then move everything to the left-hand side. Okay. So now all we're doing is we want the formula for the output is going to look like this. It's going to equal 0 if w dot x, the net input plus the bias, is less than or equal to 0. And it's going to equal 1 if w dot x plus the bias is greater than 0. Okay. So now the bias b, so b is less than 0. Okay. B is a negative number. So what are we doing? We're actually, w dot x is going to be some quantity, and then we're adding a negative number to it, so we're subtracting from that. Okay. So if we're adding a big negative number to the net input, that's going to make it harder for it to be greater than 0, right? Whereas if we're adding a small negative number, or say that's not going to affect it as much. Okay. So now the bias B, what it's doing is it measures how easy it is for the perceptron to output a 1. And we often describe that, we say that for the perceptron to fire. Okay. The idea behind fire being the same idea as when we talked about a biological neuron last time. So that's our whole sort of building block, right? So the idea is a neuron fires, it outputs kind of an electric signal to other neurons in the brain if there's like a certain input at the nucleus. And so that's the same idea here. Okay, so the basic idea here is that a big bias, and I'll clarify here that we mean big in absolute value. So a big negative number makes it hard to fire, and a small bias makes it easier. So big or small in absolute value, so just in size, right? So we're talking about a negative number here. Okay. So let's look at our perceptrons and how we could draw these now in this notation. Okay. So remember that a perceptron, so a perceptron diagram, takes kind of the following format. So we have our inputs, but then we also want to incorporate the bias into these. Let me make these a little bigger so I can write it. Okay, so we've got our inputs, say x1 to xp, corresponding to our features. But then for the bias, and we saw this last time on the first kind of picture I brought up of these, I'm going to just indicate the bias for the 1, because the bias is a constant. So the idea is the value b we're going to think of it almost as a weight, because it can be tuned and adjusted. Okay. So then we've got our net input, which is specifically the sum wj xj plus b. Okay. So the idea is from each of the inputs, including the bias, there is a weight. The weight for the bias is exactly the bias, b. x1 is weighted by w1 up to xp by wp. And so then we sum up the weights and we add the bias, and that's our net input. And then from the net input, we get an output, which is going to be, and of course I'm not going to have enough room to write it on the side here, but it's going to be a 0 or a 1, depending on whether or not, as we saw above, the net input plus the bias is positive or negative. All right. So as an example, so here are the perceptrons. Corresponding to scenarios 1 and 2 from our earlier example. Okay, so scenario 1 looks as follows. Okay, so our inputs are 1 for the bias, x1, x2, and x3. And so the bias was, now it's going to be -5. So essentially we're just changing the signs around, right, on that. And then the inputs for scenario 1, or the weights rather, were, I'm trying to fix it, 7, 2, and 2. So 7x1 plus 2x2 plus 2x3 minus 5. That's our net input function. And what does it do? It outputs a 0 or a 1. And notice it outputs a 0 if x1 equals 1, or sorry, if x1 equals 0. Because then the rest of what's left, 2x2 plus 2x3 minus 5, can never be positive. And if x1 is 1, then the net input is already 2, which is already positive. And it outputs a 1 if x1 is 1. Okay. So this does exactly what we described. And of course, it takes a lot less writing and a lot less words to draw this picture and then see what it's doing. Right? So that's kind of one of the nice advantages of these perceptron diagrams.
Julian?
Yeah.
Did we miss any greater than threshold here?
Remember, the threshold now is always 0, right? Or like, okay, so we moved everything over to the left-hand side. So the bias is incorporated into the net input, but now it's always given this way, right? So it's going to be 0 if the weighted sum, the net input plus the bias, is no more than 0.
Oh, yes,
and
yes,
it's going to equal 1 if it's
forgot this.
positive.
Yeah, I missed
so
this part. My bad.
That's the way we're doing it. That way we don't have to write the inequality in. It's always greater than 0, less than 0.
Got it. Yeah, I missed that part. My bad.
Yeah, so in this thing, basically what we're doing to determine the outputs is we're asking, is the expression in the middle, is it positive or negative? Well, positive or greater than or equal to 0.
Yeah, got it.
Okay. Let's look at scenario 2. Okay, so here, what we had was we still had a bias of a threshold of 5, which means the bias will be -5. Then our weights were 6, 3, and 3. And it gave us a net. Now our net input looks like 6x1 plus 3x2 plus 3x3 minus 5. And how will this output? It will output, well, let's see, it'll output a 1 if x1 equals, it'll be easier to just write this in the other way. Okay. So it outputs a 1 if x1 equals 1, or x2 and x3 both equal 1. And if neither of those conditions is satisfied, sorry, my eraser's not working. There we go. And it'll output a 0 otherwise. Okay. So the other two are similar, so I don't want to bore you too much, but here's a little exercise just for you to do on your own. It could be kind of helpful just for understanding. So draw the perceptrons for scenarios 3 and 4. Okay. All right, but rather than do those ones and kind of keep repeating the same stuff over and over again, let's look at a new example. Okay. So one kind of general application of perceptrons can be used to encode logic functions in computing. Okay. So this is actually, in some sense, a nice kind of example of what they can do. Rather, it's not like just sort of kind of a made-up kind of contrived toy example like the previous one. Although it's not complicated. But as we'll see, the idea that you can use these to encode logic for computing is a nice kind of general application. And we'll see later, it has some consequences, but also and leads to some natural questions. All right. So as an example of this, let's build what we call an AND gate. Let me move this down here. Okay. So the idea is what we want is a logic circuit where if both of our inputs, we have two binary inputs. And in computing, we often call these binary bits. And x1 and x2. Okay. Well, sorry, I can put them on the same line because they're going to do the same sort of thing. So x1 and x2, these are our binary bits, and they take values as usual for binary, 0, and that corresponds to false, and then 1 for true. So the idea in a logic table or logic circuit, these you want to essentially encode combinations of trues and falses, and we encode this numerically using zeros and ones. So here's the corresponding logic table for AND. So can't underline. Okay, no, okay. Keep making that one. All right, there we go. Let's stop now. Okay. So we're going to have x1 and then x2. And just so you see what it looks like, with binary bits, we just write them next to each other. So we do x1, x2. Okay. And then we'll have the result for the AND. Okay. So x1 can take the values zeros and ones. So notice I'm repeating them because I need all possible combinations of zeros and ones that x1 and x2 can take. So if x1 is 0, x2 can be 0 or 1. And if x1 is 1, x2 can be 0 or 1. So this is kind of a standard way of writing this. So then the binary, the two-part bit is either 0, 0, 0, 1, 1, 0, or 1, 1. So the idea is an AND gate should output a signal of 1, true, if both of them are true, and 0 otherwise. So the AND gate takes the values 0, 0, 0, 1, corresponding to these combinations of bits. Okay. So this, we can create then a very simple circuit. And the way we'll do this is we'll set the bias B to equal -3. And the weights on the bits, W1 and W2, to both equal 2. So what we'll draw then is a perceptron. with those weights. And so our net input is 2x1 plus 2x2 minus 3. And so then what are the outputs? The output is, let's just write them all down. So what does this lead to? This leads to okay, okay, all right, I'm not saying this very well. But, so the outputs are going to be still 0 and 1. And so then when do we get a 1? Well, if x1 and x2 are both 1. Okay. And we get a 0 if either is 0. Because if x1 and x2 are both 1, then the net input is 2 plus 2, 4 minus 3 is 1, which is positive. If either of them is 0, the net input is either -1 or -3. Okay, so -3 if both are 0, -1 if one of them is 0. In that case, then the output will be 0. So this does exactly what we want. The net input is positive if and only if both of them are 0. And that is exactly what how the AND logic function is supposed to work. Okay. So we've encoded this logic table into this perceptron. Okay. All right, let's do one more example. So let's in some sense, flip this example around. And construct what we might call a NAND gate. Okay. So in this case, what do we mean by NAND? This stands for not AND. Okay. Okay. So the idea here is what we want is the opposite of the AND gate. Okay. So the logic table is as follows. So we still have two binary bits, x1 and x2. And so x1, x2, the combined bit, has possible values 0, 0, 0, 1, 1, 0, and 1, 1. The way that NAND is supposed to work is it's 0 unless both of them are equal to 0. Okay, so in other words, it's 1 unless both of them are 1, in which case it's 0. Okay, so it's the negation of the AND. I said that the wrong way around. Okay, so not AND. Okay, so as long as one of them is false, then the NAND gate is true. It opens, so to speak. So the idea of circuits, right, is the circuits open and close corresponding to one's trues and for open and zeros falses for close. Okay, so in other words, do they output a signal through the gate to the next sort of place in the circuit? That's the whole idea behind these logic circuits. Okay, so this is actually kind of tricky then, you might think, to implement, because we want the perceptron to fire output of 1 when, say, x1 and x2 are both 0. But if you think about the previous way we had our setup, if x1 and x2 are 0, regardless of the weights are, that's going to be -3. Okay, so then it would never be positive. So how can we make this work? Okay, so now we need to be flexible. About either. There's two options here. The values, the weights, and or bias can take. Okay. Nothing in the development that we've done so far says that the weights need to be positive numbers, right? And we did say that the bias could be negative. Well, we're going to make it negative, but if you think about it, okay, so take a negative of a negative, and then you get a positive, right? So as long as you allow yourself to kind of do that kind of silliness, that's okay. The other option is we can obviously be flexible about how the output works. Okay. In other words, we can just do, we can either flip the zeros and ones, or one way to think about it is we replace the output function by 1 minus the output from the previous one. Okay. So, so for the second option, let me number these, and then I'll just mention, because we'll talk more about changes in the output function later when we talk about activation functions. For option 2, we can replace what we've been calling output by 1 minus output, okay? And then use the same perceptron structure as above. Okay, so as we will see, this really corresponds to changing what we call the activation function. So this way of doing it is something that once we've discussed this later on next week, we would be able to implement fairly easily. Okay. So this is a perfectly reasonable way to do it. But since so far we don't really have an idea of what we mean by activation function, what we'll do instead is we'll see that we can change it using the weights. Okay. So for 1, just flip all of it, just negate everything from before. So the 2 weights are going to be -2. The idea here being that if the thing outputs a 1, that makes it less likely the perceptron is going to fire, because it adds, and then what we want is when it outputs 2 1s that it doesn't fire at all. Okay. And then the bias, B, is going to be -3, so +3. Okay. So when we do it this way, our perceptron looks as follows. So we have -2x1 minus 2x2 plus 3. Okay, and so then the output is going to be, well, if x1 and x2 are both 0 or both 1, then you get -4 plus 3, -1. So it's going to output as 0. Okay, but if either of them is 0, the most that could be, or like the least it could be, is -2 plus 3 is +1. It's either going to equal +1 or +3, and so it's 1 otherwise. Okay. So it only outputs a 0 if both are true. Otherwise, it outputs a 1. That's exactly what the NAND gate is supposed to do. It's the negation of the AND. Okay. And what we'll see later is that the NAND gate is actually a very important kind of idea in computation, actually more so in some sense than the AND gate is. And so we'll see that because of this, perceptrons allow us to build any kind of logical circuit, so logic function that we like. Okay. Which is going to be nice in the sense that, okay, so it gives us, they're already a nice general framework for something. But the whole point is going to be that they can actually do a lot more. If all they were was reinventing the wheel of something we already knew, they wouldn't necessarily be the point. So it's the whole idea is that they're more than just kind of a reimagination of logic circuitry. They have much greater adaptability to much more complicated, less rigid problems than just outputting zeros and ones as opening and closing circuits. And so that is a combination of the idea that the thing can learn. Oh, I forgot to put the weights on here. So the 3, -2, and -2. It can learn in the sense of it can adjust and tune the weights and the bias, and also that the output can be more complicated than just a 0 and 1 binary. So that's all material that's going to come over the next couple weeks. All right, so last thing to mention for today is, let me pull up the tab, quiz 4 on Friday. And so this quiz covers chapter 12 on gradient boosting, and then the first part of chapter 13. So what we've covered kind of on perceptrons. I haven't written out a kind of quiz review, but what I'll do is I'll send out kind of a bullet point list of topics to focus on and study. I'll do that over an email announcement a little later today. But do look over the notes and the lectures from the last 2 class periods for an understanding of what you might get asked about from chapter 13. Chapter 12 will simply be, the quiz will cover anything that we've gone over there. And then just a reminder that the extension for assignment 2 was up to end of tomorrow. If you need any extra time, like over the weekend or whatever, just let me know. I'm happy to give you some more time if needed. And the project outline was extended till next week, so that's not due tomorrow, but you're certainly welcome to get it done whenever you want and see my email announcement about that for a few extra details on just kind of what is expected, and which the whole point was it's not supposed to be very much. It's just an idea. It's just to get an idea that you've started looking at the project, you read the description of it, you've looked at the data, you've read over what you need to do, and you thought about what kind of modeling technique at least might be appropriate for the project. So that's all. That's not due, again, not due until next week, but let me know if you have any additional questions about it.